So from our physics department, we have Ms. Trishna Charan and Dr. Ramendra Prasad, who will be showcasing some of the physics demonstration for you all. So over to you, Trishna and Dr. Raman.
Hi, hello everyone. So while Drishna is doing her setup, I will just brief you about our programs here at the university. Before that, I would like to acknowledge our students who have joined us. So we have one student who has joined us from the other island, Apimeleki from St. Bede's College from Savusavu. So thank you for joining us. This is the power of technology. We are being connected, and all the other islands are also being connected, and we can all learn and study from wherever we are. Regarding our programs here at the university, we offer Bachelor of Science programs. So you can do Bachelor of Science programs from biology and chemistry, or a combination of, say, physics and mathematics, physics and chemistry, physics and IT, which is a very common one right now, looking at the technology that we need. And we need to have these technologies to connect everyone, as well as we have environmental science programs at our undergraduate levels. So when you look at this, you must be wondering whether we will be able to get a job or not. I know it is very difficult, but yes, our students are getting jobs because all our programs that we offer are more of a practical kind of programs, not just a theoretical like we have been demonstrating. So our students have been working as analytical chemists. We talk about air traffic controllers. They are there controlling our airplanes. Now that the planes have resumed, so they are there doing that. They're working as forecasters with Fiji Met Services. There are energy officers as well, who are our students. Students are working with Sugar Research Institute of Fiji. These are all of the places, not just all of the places. There are some of the places where our students are working. And if you also want to further studies, and you want to go and become something else, like one of the students just recently called me and said, say I want to become a lecturer, and what is the pathway that I want to choose. So that's, we have to guide you, because you have to take a first degree and then step by step go and do your postgraduate level studies, do your master's level studies, and we will not leave you there until you reach your goal. So that's what one of the assurance that I want to give you when you join us here at the university. We will guide you throughout, and if you face any problem during your career path as well, you can always contact us. Students during this pandemic, some of them were on reduced hours, etc. They usually come and talk to us, and we used to counsel them and tell them, okay, this is just one of the problems. It is going to pass, and there are these options that you can select, and you can always upgrade your skills so that you become more marketable, rather than just sitting there and thinking about what to do. So we are always there. We will not leave you. That's one of the assurance that we want to give you from the University of Fiji side. If you join us, we will be there always to support you in any in whatever way we are able to do that. Thank you for joining us. And we also have another student who is joining from Sacred Heart College, which is also, I think, in Bua, if I'm not wrong. Right, so that's good. Good to know that students are joining from all over the place. Over to you, Dishna.
Right. Thank you, Dr. Raman. Hello, everyone. My name is Trishna Charan, and I take physics at the University of Fiji. So, Dr. Raman has introduced you to some of the programs that we offer. So, for the physics program, we have a wide variety of courses, ranging all the way from classical mechanics. We look at quantum mechanics, and then we go on to look at energy, environment as well, atmospheric physics as well. So we have a rather wholesome package of programs. And if any of you, if you're thinking of joining the physics stream, the possibilities of you getting a job afterwards, like Dr. Raman has mentioned, it's high, right? Because there's a lot of demand for physics graduates. Right. So beginning with the lab demonstrations. So physics, just like any of the other science courses, really, we do need experiments to verify many of the theories and concepts that we learn in the classroom. Now, again, because of the COVID crisis, such kinds of situations, we will not be able, we do not have the opportunity to have face-to-face lab classes. But in Beyond Labs, we have a lot of online experiments, online labs that can be done right? And this is true for physics labs as well. So I'm just going to quickly share my screen with all of you, and let's look at some of those labs. All right, so on your screen right now, you'll be able to see the different kinds of streams of labs which are available for you to do online on Beyond Labs. So we have mechanics, density, optics, circuits, quantum, right, calorimetry, gases. So all different branches of physics, right? So we have all different types of labs which is available. So let me just click on some of them to show you the types of labs that we can do. So I'm just going to go into mechanics first. Okay, let it load. Right, so in mechanics, we have so many options, right? We can introduce, for example, rams. We can introduce different kinds of objects. We can apply different type or different direction of forces on them, and then we can investigate how it's going to affect the movement of these different types of objects, right? So you can, for example, see force vectors over here pointing in different directions. We can see inclined planes. We can place the object on these inclined planes, and we can investigate how it moves down that inclined plane, right? So those are some of the things that we can do under mechanics. And then, for example, we have circuits. If we go on to look at the circuits lab, it's loading. So we have a breadboard. We can simply connect electronic components onto the breadboard, and then we can measure, for example, what its voltage is, what its resistance is, what is the amount of current which is passing through these different components, right? So that's something that we can do in the circuits labs as well. And then we have quantum, right? So we have a lot of quantum labs, right? So we can set up, for example, let me just reset the lab, right? So what we can do is we can investigate using all of these different types of equipment which is available. We can set up the experiments ourselves. We also have presets as well. So these presets, they allow us to select a particular activity sheet and work according to the instructions given in the activity sheet. Right, so I'm just going to exit this. Let's start off with a very simple experiment. So let's go on to mechanics, right? So under mechanics, we have, for example, kinematics. So we can measure speed, we can graph, right? We can look at accelerated motion as well. So let's just have a look at this one. Right, so it's loading. Right, so what do we have here? So we essentially have a ball. You see that? It's located right on the top of an inclined plane. What is going to happen when the ball goes down this inclined plane? Of course, as it's going down, its velocity is going to increase. It's going to accelerate as well, right? Because there's this force of gravity which is pulling it down. So it's going to have a certain increasing velocity as well as acceleration. So when we use stimulations like this, it allows us to record what is the velocity, what is the acceleration, what is the distance, for example, that this ball is covering while it is going down. So we have that being recorded each second, right, per time in real time. So for example, let's have a look at the parameters, right? So we can, for example, change the object we are using. So in this case, we have a plastic ball, for example, right? And it's going down the inclined plane. We can change its mass, for example, as well, right? We can change the different friction, the amount of friction that we can apply on the inclined plane. We can change the gravity. Are we looking at this on Earth, or do we want to go on the moon and investigate how the ball is going down, right? We can play around with forces as well. We can play around with the angle of the inclined plane as well. So there's so many parameters which we can change and then see how this affects how this is going to affect the movement of the ball as it's going down the inclined plane. So let's just start off with, let's say, our baseline, right? Let's see how it actually works. So there's some things we might want to note down. For example, we might want to note down the particulars of this ball before it starts to go down the inclined plane. First of all, let's note its mass down. So it's a 10 kg mass, right? It has a 10 kg mass, and the surface, let's say the surface, we keep that as plastic, and the ball we keep that as plastic as well. So the friction coefficient is a fairly small one, 0.15, right? We're doing this on F, and we're keeping the inclined plane at an angle of 30 degrees, right? We're keeping the inclined plane at an angle of 30 degrees. So let's start off, right? I'm going to press on the start button and the ball will start rolling. Okay, so before we do that, what are some of the predictions that we can make? Of course, we can say that as the ball is going down, it's going to accelerate, and its velocity is going to increase, right? So those are some of the things that we can already note down. And yes, its initial velocity is 0. That means when it's right at the top of this inclined plane, it's not moving, right? Its initial velocity is 0. It is at rest. So if we press on start, let's see what happens. So the ball starts to go down the inclined plane. And while it is going down the inclined plane, let me just run that stimulation again for you. You'll be able to note down how its distance is going to vary. So it starts off at around 50 meters. It's a 50-meter inclined plane. You can see that the velocity is increasing, and it has a constant acceleration of 3.629 meters per second squared, right? And these are because the ball is going down, translational motion, as well as rolling while it's going down the inclined plane. You'll see that we have both the rotational values as well as the translational values. So velocity total, it refers to the final velocity right when the ball is at the end of that inclined plane. So now let's try to investigate, let's try and vary one of those parameters. But before we do that, let's record some of the things over here. We have a feature in Beyond Labs, which is known as Labbook. You can click on this. Let us quickly note down some of the parameters that we selected. So we were looking at a 50-meter run, and we're looking at a mass of around 10 kg, and we were looking at a friction of 0.15, and we're looking at an angle of 30 degrees, and we had initial velocity is equal to 0, right? So these were some of the things that we were investigating. Now let's just change any one of the parameters, right? So whenever we want to investigate, for example, how is the mass of this particular object going to vary or going to change its time, or the final velocity or the acceleration it's going with, we have to ensure that we only change the mass and none of the other parameters. So let's do this. Right, so I'm going to change its mass. Let's change the mass. Let's bring it to only 1 kg, right, to see exactly what kind of difference in results we get. Let's keep other things constant, right? That means it's still going to start off at rest. The angle of this inclined plane is still going to be 30. It's still plastic on plastic, right, and it's still on Earth. So we've just made one change, and that is we've changed the mass of this ball as it's going down the inclined plane. Now, if you do physics, you would already be knowing this, right? Does the mass of this ball affect the movement of this ball as it moves down the inclined plane? What do you think? Let's find out, right? Let's find that out. So it's moving down, we can see the time changing, right? The time, if you recall, when we were doing it for 10 kg, was the same. The final velocity was the same, and the acceleration value that we see here was also the same value. Right? So these were the values that we were getting. I might as well take a screenshot of this for you right now, so that we can always refer to this, right? So what did we learn? We learned that mass the mass of this object, the mass of the object that is going down the inclined plane does not affect the time it takes for that object to completely go through the inclined plane. The velocity is unaffected, as well as the acceleration. So these things are not affected when we change the mass, right? Now let's try with some other parameter. Okay, so I'm just going to quickly reset this and let's click on parameters again. So remember, our initial baseline is when we're looking at 10 kg, 50 meters, the friction coefficient is 0.15, angle is 30, and initial velocity is 0. So now what we do, let's change some other parameter. How about we change the angle of this inclined plane? So instead of looking at the 30-degree angle, let's just go and increase this angle. Let's increase it to, let's say, how about 45? Let's see what happens. So let's press on that. Change this. A moment. Right. Okay, let's try changing the friction coefficient, right? The angle, we can look at the angle a while after. So let's change the friction. Okay, how do we change friction? Let's get a really high friction coefficient. Let's say wood on wood, right? So that means we're looking at a wooden object which is on a wooden surface. So you can see the friction coefficient increases significantly. So we have a value of around 0.55, right? Everything else, okay, in place. We have to ensure whatever our baseline was, right, is met. The only parameter that we are changing right now is the friction coefficient. What are some of the predictions? Well, some predictions would be time would be increasing. I would predict the velocity, final velocity to decrease, and the acceleration value. Let's see what happens. So the ball is rolling down. As you can see, it's rolling down a bit slower. Right, so we have a time of 5.83. Just investigate that with our initial time of 5.24, so it takes longer. It has a smaller final velocity when it reaches the end of the inclined plane, and it has a smaller acceleration as well, right? So what can we say about friction? So when we have increased friction, it's going to affect the velocity, it's going to affect the acceleration, it's going to decrease both of these quantities, and it is going to increase the amount of time for that object to go down the inclined plane, right? We can also, like I mentioned, play a bit around with the angles as well as the initial velocity. We can take this to the moon as well. So let's just take it to the moon. See what happens, right? This is something we can not do in our labs. We can't take our experiments on the moon. Well, at least, beyond labs allows us to do that. So what do we know about the moon? We know its gravitational acceleration. The force of gravity is weaker. If I were to just go over here, let's just select moon. You can see Earth has a gravitational acceleration of 9.98 meters per second squared, whereas moon just has a gravitational acceleration of 1.625 meters per second squared. So significantly lower values of gravitational acceleration. So I'm going to press on start again. If this were an inclined plane on the moon, what will we see? Okay, can you see it's moving really slowly? The reason why it's moving really slowly is because the force of gravity is very small on moon compared to the Earth, right? So you can see it takes a significantly longer time to move down, and that is a value of around 12.89 seconds. And then the final velocity is smaller as well. This is because the gravitational acceleration is smaller. The gravitational acceleration and acceleration, it represents how the speed is changing per time. So how is speed changing per second, right? That is going to be the pull of the gravitational force. So if the gravitational acceleration value is smaller, then this obviously means that the rate at which the speed is going to be increasing is going to be smaller as well. And you can see the final velocity value is small. It's just of 7.8, and the acceleration is 0.6 meters per second squared. If we were to compare that to the Earth, right, keeping all the other things, same, you will see that the time increases, velocity decreases, and the acceleration decreases. So that allows us to find some type of relationship between time, velocity, and acceleration and gravitational acceleration. So in this way, you can change all the other parameters and investigate how these parameters are going to be affecting the movement of a ball as it moves down the inclined plane, right? Okay, so that is about mechanics. Why don't we go and investigate some other field now? So we are going to click over here. So this now brings us back to some of the other experiments that we can do. How about we look at circuits now, right? Just try to draw a simple circuit, right? Electronic circuit, and try to measure what the voltage values is and what the current values are for all of these electronic components that we are going to put in. So right on your screen, you should see a breadboard. What is a breadboard? Well, of course, those of you who take physics, you know what a breadboard is, right? It's just a rectangular plastic board with a lot of holes in it, right? And we use this breadboard, we insert electronic components in it, right? And we make a circuit, and then we can measure the amount of voltage and amount of current which is moving in these different electronic components. So what kinds of electronic components do we have here to select from? Well, we have resistors, right? You can see we have inductors, we have capacitors, we have wires, we have bulbs as well, right? Now the thing about using this circuit stimulation is we can do two things. We can draw it over here, we can draw the circuit diagram, and Beyond Labz will automatically build that circuit for us on the breadboard. Or we can connect these components onto the breadboard, and the stimulation will simply draw out the circuit diagram corresponding to what you have inserted over here on the breadboard. Right, so I'll give you an example, for instance. So we have a resistor. So we'll just take one resistor over here, place it. As soon as you place a resistor, that resistor gets placed on the breadboard automatically. Let's place another resistor over here, for example. We place another resistor. You can see another resistor gets inserted into the breadboard. Let's again place another resistor over here. There you go. So we have 3 resistors at the moment. Let's connect them now. Right, at the moment you will see they are not connected on the breadboard, right? These resistors are not electronically connected to each other. There is no wires which is connecting them at the moment. So let me add some wires, connect these 3 resistors together, and let's connect it across a battery as well. So this is our battery. As soon as I bring the battery in question, you can see the LEDs automatically pile up on the connect to the bus. Right, this is known as the bus area, or rails as we call them as well. Now let's just let's just connect wires. So as soon as I go near any one of the resistors, this blue dot becomes highlighted. So I'm just simply going to drag that and connect that. As soon as I do that, you can see some of the changes are taking place already. Right, there we go. So what have I done? I have just simply connected 3 resistors and I've connected them in series. And when I've done that circuit diagram, there's going to be an automatic connection of all of these resistors on the breadboard, right? So we can do that. Why don't we ourselves create a series, circuit, and then we can measure what the different values of voltage and current is, right? So let me just press on Reset Lab over here. As soon as we do that, you'll see all the components disappear. So let us connect it ourselves. So let's start off with the resistor. Before I do that, let me quickly tell you a bit about the breadboard. Right, so in a breadboard, we have all these holes, and some of these holes are going to be connected to each other, right? So electronically connected to each other. So for example, if we have a look at 1A, B, C, and D, these 5 holes, these are connected electrically to each other. That means there's simply going to be clips under this, metal clips, and the metal clips are going to be connected, right? And the same goes for this row, right? That's going to be electronically connected to each other as well, and that's going to be the case for all of this, right? So there's a electric connection between all of these holes, right? So for this this row as well, this row as well, then you can see there's a plastic divider. Like I said, it's made of plastic. So you have a plastic divider over here, and then you go into the second section, and then you have rows over here as well. Same thing, these holes are going to be connected. The holes in this row is going to be connected. Same thing over here, and for the other rows as well. But this row is not going to be connected to this one, right? And this row is not going to be connected to the other as well, because there's a divider in between them. Okay, and then you might be asking about, what about the lengthwise strips? Well, the columns, these are not connected. It's only the rows which are connected. So for example, 1A, 2A, 3A, 4A, 5A, 6A, these are not going to be connected to each other, right? So whenever we insert any resistor, we have to ensure that they end up in holes. Each leg of the resistor ends up in holes which are not going to be connected to each other. If we do that, let's see what happens on the circuit diagram. See, if we place it in 2 holes which are connected to each other, this is the kind of diagram which which comes up, and that is something that we don't want to do. So let's take this resistor out. Let's try with another resistor. Let's place it on the second breadboard here. Okay, I'm going to drop it. Let's place it. So there you go. Right, so that is one resistor. It appears right at this location. How about we connect another resistor? Right, so just place it anywhere. We're trying to connect this in a series, so I'm just going to place it like that. How about we have another resistor? Let's just place it somewhere. Make sure the leg is not connected. And there you go. And you can see that the diagram over here gets automatically created for you. But at the moment, you can see it's not connected to each other, right? The resistors are not connected. How about we change the values of these resistors a bit? So let's keep that as 100. Let's change this to, let's say, 220, right? For 200, 220 ohms, right? There we go. Let's just change this to maybe 280 ohms, right? So there we go. We've changed the value of these resistors. Now let's connect them. So let's use wires over here. Let's place one wire at this location and another wire at this location. So you'll see that these 2 resistors become connected. The way it might be a little bit weird for you when you see this circuit diagram, and that is because the way in which the diagrams are placed, the resistors over here, for example, that's laid horizontally, this resistor is laid vertically, and that is why it appears to be that way. But if we were to look at it, it's just one resistor connected to the other resistor using wires, right? Using a straight wire. So now what we've done is we have in fact connected these 2 resistors together. Let's connect this resistor with this resistor now. So again, we take a wire, we place it at one portion there and another one there. So now these 2 resistors become connected. Now let's just connect it across over here, right? So this is what we call the bus, right? Or the rails, like I mentioned. This is where we connect our battery or an external power source, right? We can actually connect it anywhere on the breadboard, but at least when we have a separate, when we have a separate set of rows and columns for the battery, the external power source, it allows us to be more accurate, and it's a safe practice as well. So let's just quickly connect this, right? So I'm just going to insert it over here. Let's connect this to the negative, and let us connect this to the positive. Anywhere, you can place it anywhere. Now, there's a bit of difference between how the holes in the buzzes are connected compared to how they're connected in these sections. For the buses, right, or the rails, the holes are connected, electrically connected down the sections and not across the rows, right? So it's a bit different. So again, all of these holes are going to be connected in the bus. These 2 points are not going to be, the rows are not going to be connected, right? So that's one difference. And that allows us to be a bit safer when we are drawing these different types of, or when we're making these different types of circuits, right? So the red usually indicates the positive and the blue or the black indicates the negative. So I'm just going to place this to the positive. Just give me one moment. Right, there we go. And this gets to the negative over here. There we go. Right. Let me just, one moment. Get back here. Let's just switch this off for the time being. Right, so what have we created? We have created a series circuit. We have 3 resistors which are connected in series. What we can do now is we can use the multimeter, for example, over here, in order to measure what the resistors values are. What is the resistance is of each of these resistors? We can do that. We already know how to. We already know what the values are, right? Because we've just we can look at the circuit diagram and figure that out. But why don't we use a multimeter in order to find out the resistors and see if it's the same value, right? So what we usually do is we place the LEDs at this location, right? So let me just start off with this. Place it over here. Place the other LED at this location as well. Yes, so you can see it has a bit of plus or minus, the value. So this is around 100.2 ohms. So this is our 100 ohm resistor, right? And we can use the multimeter to measure the value for resistance for all of these resistors. So let us do that quickly, right? Very close to 220, we get 219.8 ohms. Then we can go on to our third resistor, and likewise we can measure what the value for this is. This is 279.5, very close to 280 ohms. Right, now what we can do also is, let me first of all remove this. We can also allow some, we can turn on the voltage, apply some certain amount of potential difference across these resistors. So let's turn on our battery. There we go. So it's at 4.5 volts. We can increase it to, let's say, around 9 volts, right? So that is the amount of, that is the amount of voltage that is being supplied by our battery over here. It's going to go through the buses, and through the buses, it's going to go through all of these resistors which are connected in series. Now, what we are going to do is we are going to measure what is the amount of voltage which is flowing across each. What do we know about series connections? We know that when we have resistors which are connected in series, we know the voltage is going to divide, the current is going to stay the same. So let us investigate that. So we start off. So whenever we put the LEDs, the multimeter also has a positive and a negative terminal, right? So the red represents the positive. So we are going to be connecting that across over here. This is connected to the positive terminal of the battery. So we are going to put the positive LED of the multimeter at this location. And the other side is, as you can see, connected to the negative. So we're going to put that and bring that over there, right? And let's quickly, okay, there we go. So out of that 9 volts, 1.51 volts is flowing across the 100 ohm resistor. And in the same way, we can measure what the voltage is going to be for all the other resistors, right? How about, since we are over here on resistor 1, we measure what the value for current is. Now there's a difference in how you measure current and how you measure the value for voltage. When you're measuring the voltage, similar to how you're measuring the resistance of a particular resistor, you just simply take your LEDs, right, the multimeter LEDs, and you place it on the other sides of the resistor, just like it's done in this case. Right, so you're basically tapping in and trying to find out what is going to be the voltage which is dropping in, right? So you just go and insert your LEDs in this manner, just tap in. But when you are measuring the amount of currents, it's going to be a bit different. Can you see the LEDs moved over here? That is because in order for the multimeter to measure what is the amount of current which is passing through the resistor, all that current needs to go through the multimeter as well. So that is why it's a bit different. So you're actually making the multimeter a part of your circuit, right? Whenever you try to measure what the current flowing across a resistor is. So you can see that it's around 0.015 amps, right? We're creating a DC circuit. So current DC is around 0.15 amps, right? So what we can do now is, okay, let's test this, statement that we made, and that is that the amount of current is going to be the same. So I'm just going to place it over there. Yes, the other resistor, even though it has a higher resistance, it has the same amount of current which is flowing across it. Now let's do the same thing for the third resistor. Same amount of current is passing through it. Why don't we look at what is the voltage which is passing through it? So I'm just going to change this over here. Let's investigate again what is the voltage which is passing through. We do that. We know for the first one it was 1.5. For this one, let us quickly measure that. That's around 3.3. And for this one moment. Right, so we have 4.2. If you add up all of this, it will be 9 volts. So yes, voltage does divide across series connection, and yes, the current does stay the same across resistors connected in series, right? Just to give you another note, if we try to connect the LEDs otherwise, let's see if I connect it over here. Let me see if that's possible over here and over here. It gives us a negative value, right? Because in this resistor, this end you can see is connected to the negative, this end is to the positive. And if we reverse it, if we connect the multimeter with this end, which you can see is connected to the positive, but if we connect the negative terminal of the multimeter over here, right, and the positive on the other end, which is connected to the negative terminal of our bus, you'll see it gives us a negative value. It gives us the right magnitude, but you'll see a negative over here because we've connected the terminals incorrectly. So we need to ensure that that does not happen, right, and we connect it properly. It's not going to harm the circuit in any way, but it's just good practice to connect it properly, right? So just check which of the ends is connected to the positive terminal and which of the ends is connected to the negative terminal, and then you use your multimeter in order to measure the values in the same way, right? So what we see over here is a series connection of resistors, and we've measured the current, we've measured the voltage, we've measured the resistors, a resistance of each of these resistors using a multimeter. And in the same way, we can create parallel circuits as well, right? So now let's just work with the same set of, let's say, resistors, 100 ohm resistor, 220 ohm resistor, and 280 ohm resistor, but we connect them in parallel now. So how do we do this? Well, again, we start off with resistors, right? Again, we can connect them anyhow. When I connect them like this, they are not going to be connected, right? These holes are not connected to each other, so that's going to be fine. I can place them like this. Let's just have another one. Make sure that, right, there we go. So you want to make sure that the legs are in the same row. So that means we will be able to connect these two resistors in that way, right? So these two resistors are going to be connected because the legs end up on the same rows. So see, you can see that's the kind of diagram that we get. Now let's not have such a large value. Just have a smaller value of this. Yeah, one moment. Reset this. Let's try again. So we have a small resistor over here. Place it in this way. Another resistor at this location. There we go. Right, so we have two resistors. Clear that. Try again. One. And another one over here. And then we have another one at this location. And there we go. So now you will see these two resistors, this one over here and this one over here, they are connected to each other. But the third resistor is not connected to these two resistors. So what we can do quickly is we can connect it across these resistors and then connect it across over here as well, right? So we can do that in order to form our parallel circuit. So let me just go over here. Let's place it at a different place so that we can have enough holes in order to put the wires in. So there we go. Ignore this. This is just an additional thing that pops up. It's not part of our circuit, right? And then we put one over here, right? So now let's connect this resistor to that resistor, connect it, and let's connect this resistor to that resistor. So 1, 2, 3, right? This one, and this one. This is our 3 resistors which are connected in parallel. Then what we do is we connect one of these resistors, connect it to, let's say, the negative terminal of the battery, and the other resistor, the other end to the positive terminal of the battery. Now you might be wondering, why isn't the battery appearing over here? Because we haven't connected it yet, right? So let's just quickly do that. This is the positive, and this is going to be the negative. Now you'll see the battery comes. So what do we have? We have 3 resistors, 1, 2, and 3, which are connected across the battery. So just ignore this one and this one. This is just a reflection of the resistors. It's not part of our circuit, right? So we have 1, 2, 3 resistors. Now let us again turn on the battery, 9 volts, right? How about we change the values a bit? Let's again get 220. Okay, and let's get 280, similar to what we did last time, 280. And there we go. So we have 3 resistors which are connected across parallel connections. And again, what we can do is we can measure what is going to be the voltage and current across this. So let's start off with measuring the voltage. So again, because this is connected, this end, this leg of the resistor is connected to the positive of the battery. So that's where we place this. In one moment, and the negative to the other end, like so. 9 volts, right? Just as we expected, because when we have resistors connected in a parallel, the amount of voltage is going to be the same. It's only the current which is going to divide. So what we can do is we can change the setting, we can change the dial on the multimeter and simply at the same time measure what its current is going to be. Current is 0.041 amps. And you will see as I measure what is the voltage and current across each of these resistors, that the value for voltage will remain the same, but the value for current will change. Right. So let us again go into this other resistor. Just place it. So you can see the current values. You can use this in order to measure what the current values are going to be. And you can see current divides. So it's not going to be the same. The total amount of current is going to divide when it flows across parallel connections. Right. And in the same way, we have the voltages, right? We can check what the voltage connection is. Let me just bring that tab there, right? So we have 9 volts. The first resistor also had 9 volts, and the second one is also going to be having 9 volts, right? So each one of these resistors, they have 9 volts of voltage passing through them, and they have varying amount of current depending on how large the resistor is going to be, because a larger resistor is going to draw in a larger value or larger magnitude of current, right? So you can try this with different values of resistors. You can try this with different values of with different values of the amount of power that you're applying to this, right? And try to investigate what is the amount of current which is flowing across each one of those resistors, right? You can have more complicated circuits. You can make more complicated circuits and then try to do the same kinds of experiments, measure its voltage, measure the value of its currents, right? And you can make essentially record that. What you can also do is you can vary the amount of voltage which is passing through, right? You can do that, and again you can vary how, what is the amount of voltage that's going to be there, what is the amount of current that is going to flow across a particular resistor, and that will allow you to make a graph of voltage versus current, and allow you to verify the Ohm's law, right? So those are some of the kinds of experiments that we can do using circuits section in Beyond Labs, right? So let me just exit this lab now, right? And that's it. Let me just stop sharing now, and let's get back. Right, so that's it from the physics section. Thank you all for listening in, and I'm going to pass it over to our host now for the chemistry section. Thank you. If you have any questions, do let me know. I'll answer them in the chat. Right. Thank you, everyone. Over to you, Zafia.
Okay. Thank you, Krishna and Dr. Raman, for that overview of physics demonstration. I'd like to welcome our participants, Elda, Shivantika, and also Nazimun. Thank you for joining us. So we just finished our physics demonstration. I hope you were able to understand whatever was being demonstrated. Felipe, I saw that you had registered your interest for physics demonstration, and thank you for the feedback. Indeed, Trishna did an excellent job in demonstrating the labs. Now moving on, before we move on, those of you who has joined us now, please fill in the attendance sheet through the chat box. So we have shared the link for your attendance in the chat box. Please fill in your attendance, and then we will be able to use that to provide you with the certificate as well.